So the exponential distribution has a property that's called memorylessness. So what this means is essentially the following. It doesn't matter how much you already weighted, how long you waited. How long you waited already, that is, in terms of when the next event happens. So let's make this precise using an example. So here's the example. In your book, this is 4.59, 4.60 in Navidi 5th edition. So this says that the lifetime of a particular integrated circuit has an exponential distribution with mean 10 years. So mean lifetime equals 2 years, equals 2 years. Okay. So you let t be the lifetime. Mu t equals 2, and this implies that lambda equals 0.5. That's the parameter for the distribution. So t is distributed as exp 0.5. All right. The question asks to find the probability that the circuit lasts longer than 3 years. So the probability that t is greater than 3 years. So this is, we can use the CDF for this by saying that this is the same as 1 minus the probability that t is less than or equal to 3. And now we have our equation that is the CDF over here, right there. This equation is the CDF, so we can use it. 1 minus e to the negative lambda x. So to solve this, we have 1 minus, plugging in our CDF, 1 minus e to the negative lambda, 0.5 times 3. The ones go away. We're left with e to the negative 1.5. Evaluating this, it's equal to 0.223. Okay, so that's just one calculation. So moving on to the next example. So you suppose the circuit is 4 years old. Already. So you might think that it is more likely to break, but that's not the case, as we'll see here. So we can we want to check. Now the problem is to find the probability that circuit lasts for 7 years. Now the circuit lasts for 3 more years. Circuit lasts for 3 more years. What we're looking for. So this is the same as the probability that t, our original time, is greater than 3 plus 4, which equals 7. given that t is already greater than 4. So it already lasted 4 years. That's the probability we're interested in. All right. So we can apply the definition of conditional probability. This is equal to, go over here, the probability that t is greater than 7 and t is greater than 4, given over the probability that t is greater than 4. So if t is already greater than 7, then we know it's greater than 4, so this is just the same as the probability that t is greater than 7 over the probability that t is greater than 4. Okay, so we can apply the same result from up here, this expression that we get, this one right here, to top and bottom. So we have e to the negative lambda 0.5 times 7 on top. That's the probability that t is greater than 7 over e times negative 0.5 times 4 years. All right, this is the same as e to the negative 0.5 times 7 minus 4, which is e to the negative 0.5 times 3, e to the negative 1.5, which we saw up here is equal to 0.223. Okay, so this is the same. Okay, so that means that knowing that it's 4 years old already didn't change the probability that it lasts for 3 more years, which is really weird and unintuitive if you think about older things being more likely to break. If it follows an exponential distribution, if the lifetimes follow an exponential distribution, then they are not more likely to break if they're old. Okay, we can write it out in general. So here's the general property. Generally, if we take t distributed as exp exponential lambda and little t and s positive numbers, then probability that t is greater than little t plus s, given that t is already greater than little s, this is equal to the probability that t is greater than a little t. And that's the general statement of the memorylessness property.